All right, you ran a two-group experiment. You collected two means. How do you make inferences about the population mean difference? In addition to knowing you collected two means, you have to know what your experimental design is. So if you have a between subjects design, you're going to use the independent samples t-test. You know what? If you want, feel free to call it the between subjects t-test. Now, how do we know that we have a between subjects design? Now, this is something I'm assuming you remember from the previous course in this sequence. But essentially, were your participants randomly assigned to one of two conditions? If they were, that's a between subjects design. If your participants participated in both conditions, you know for certain that is a within subjects design. So between subjects design, you have different participants assigned to different conditions. And if you have that, if you have a between subjects design, you use the independent samples t-test. Participants are randomly assigned to conditions. Okay, what's today's lecture plan? The first section, the first 3 bullet points are how would you analyze data in the real world? The fourth section is there's a few new concepts that I have to teach you, so I'm going to teach those to you. But I'm going to show you that you already have the conceptual knowledge to interpret this data, even though you don't know the t-test, even though you don't know degrees of freedom yet, even though you don't know pooled standard deviation. Everything I've taught you up to this point will allow you to get the full picture without knowing those details. The first step in any analysis is getting the numbers we need. So I'm going to share with you one of my recent experiments. I recently ran the following study, and I'll talk about it a little bit. I believe that our common methods of discussing prejudice actually make people less likely to believe that they have free will over their prejudice. What we know about beliefs in free will outside of prejudice is that if you believe you don't have free will, you try less hard. If you believe you don't have free will, you're more likely to cheat because you don't control your behavior. These are actual findings from the field. So I'm trying to think about how we talk about prejudice when we're trying to get people to change their behaviors or their beliefs or their attitudes to create, a less racist world, because that's the goal of the research that we do on my side of the psychology neuroscience divide. And ultimately, we tell a lot of people everyone's prejudiced. You need to acknowledge this. You need to accept this, right? With the idea that telling people that everyone's prejudiced, that will make them more likely to change their behavior. But at the same time, that free will information sticks with me. If everyone's prejudiced, we don't control it. It comes from our environment. Shouldn't that, then I'm not responsible for this. I didn't control this. I didn't create it, right? So I wonder if that message, and I really do, I wonder if that message is reducing beliefs in free will over prejudice, with the assumption that in future studies, I'm going to examine if that reduction in beliefs in free will reduces motivation to reduce prejudice and that thus increases prejudice. So that's the research that I do. This is an actual project that I'm working on right now. So let's just sort of give you the experimental design. It's a between subjects design. Participants read either a fake science paper that stated everyone is prejudiced or one that stated everyone can overcome prejudice. You now understand where I'm coming from. They completed a 7-item belief in free will over prejudice scale. I averaged the responses together. I'll show you how to do that in a different lecture. I ran some other measures. It's all not important for this class, so we're just going to focus on the manipulation. Okay, everyone is prejudiced article, or everyone can overcome prejudice, and the measure. Do I have free will over my prejudice? I essentially converted a belief in free will scale to a belief in free will over prejudice scale by changing the words like action to prejudice, behavior to my own racism, stuff like that. I made those logical insertions. Let's see the data you're going to be working with today. There are many ways to present data, but for me, with the between subjects design, I often just present my data in 2 columns. One column for group 1, one column for group 2. There are multiple ways to present data, and I'll show you another way when we use our computer program, but this is just our data. So we're going to try to run analyses on this data. What are we trying to calculate? Let's see that in the next slide. We are trying to calculate our means because we want to know which mean was larger. right? We need to know the means to test to get a basic sense of our hypothesis. Not to test it, but to get the basic sense of, do our data basically support this hypothesis? Standard deviations, these are now Bessel-corrected standard deviations. All that means is you divide by n-1 instead of n, because that gives better approximation of the population standard deviation. That's the explanation. That's the change. That's the new thing. Standard deviation before, where I divided by n, we now divide by n-1. We're going to calculate our mean difference. We know why. We're going to calculate our average standard deviation. This is now called pooled standard deviation. I will explain this later. Cohen's d, we know. 95% confidence interval of the mean difference, we know. 95% confidence interval of Cohen's d, we know. T-statistic, I will explain that later. We don't need to know it. What you need to know is it leads to a p-value, which you already understand. Degrees of freedom, this is new. It's actually not that important, but I will explain it because it comes up. And then finally, p-value, we need to know that too. Is our true population mean difference 0? No, or I don't know. Okay? So, and of course, 95% confidence interval, the mean difference, the true population mean difference likely falls in that range, right? So we're going to just do these calculations, and I'm going to show you how. So we can actually get all these calculations done in less than 5 minutes, and I'm going to show that to you, show you how to do it. I do know that there are 2 versions of SPSS running around our class. Some people had access to SPSS at home. Some people found a workaround. If you have an earlier version, not the one we downloaded for this class, we downloaded 27, you won't get the Cohen's d data automatically, and there is going to be a slide at the very end of the lecture that shows you how to get that Cohen's d data, okay? So you're just gonna have to sit tight and realize you're not gonna have that Cohen's d data. But right now, I'm gonna go ahead and do those calculations. All right, so how do we do our analysis using SPSS? How do we get our calculations the way a professional statistician would? It's pretty easy. We wanna know the true population mean difference, and so we're going to run an independent samples t-test with all the statistics we talked about already. So we already know what we're doing. How do we get there? So I know this is not the first time you're looking at SPSS, but you can look at the data view and the variable view. There are 2 views for an SPSS data file. I'm just going to focus on the data view for right now, and I want to get my data completely entered into SPSS. There is one rule for entering data in SPSS. 1 participant per row. That is it. Okay? So, when we're looking at our data, it's over on the right. We can see all 8 of our dependent variables, all 8 of our observations of our 1 dependent variable, belief in free will over prejudice, that score. So we can easily see that. We can see 8 numbers. Those 8 numbers are going to have to go into SPSS somewhere. Additionally, what you see is that it's not really represented by a number, but you've got another piece of information that needs a number added to it. So we have the everyone is prejudiced group. Half the participants are in that group, and the other half are in the everyone can overcome their prejudice group. So for right now, what I'm going to do is just, for each participant, I'm going to enter in 2 numbers. The first number I'm going to enter in is what condition they were in. The second number I'm going to enter in is their score on the belief in free will over prejudice scale. So 1 equals everyone is prejudice, 2 everyone can overcome prejudice. So there we go. 1, 3, 1 person per row, I'm done with that row. 1, 2, 1 person per row, I'm done with that row. 1, 1 person per row, I'm done with that row. 1, 3, 1 person per row, I'm done with that row. Now, done with those 4. On to the next one. So what condition were they in? They were in the different conditions, so they're in 2. Their DV was 5. 1 row, 1 person per row, I'm done with that row. 2 and 3. 1 person, I'm done with that row. 2 and 4, 1 person, I am done with that row. And 2 and 4, 1 person, I am done with that row. Okay, so now I got all my data entered. However, I want to make my outputs really easy to interpret, really pretty. So I'm going to go into the variable view and I'm going to change a few things. First thing I'm going to change is the name. the name of the variables. The first one's going to be my manipulation. The second one is going to be beliefs, free will, prejudice. That's good enough for me. Okay? Now, for my conditions, I really do like to use value labels. So value number 1, I typed in 1 for everyone is prejudiced. So everyone is prejudiced, add. Value number 2, I typed in a 2 if they were in the everyone can overcome. So everyone can overcome prejudice, add. So that's the first thing I did. I don't do that for my dependent variable, just my independent variable. And then finally, the last thing I change, which is more probably just to be in line with how lab is running, is I make sure that my independent variable is nominal and my dependent variable is a scale variable. Okay? Dependent variables are measures. Independent variables are manipulations. I like to say the phrase, this causes that, right? So we know independent variable and dependent variable, I really, really hope by now. But your independent variable is your manipulation. Your dependent variable are all your measures. And you can have more than one manipulation, more than one measure. So now I'm in my data view, and I want to show you something. View, value labels. And then I want to show you can make the cells bigger. Now I'll just double check my data. Everyone is prejudice 3. Perfect. All my data looks great. Now, how do we get our data analysis? Let's go through the steps. Up at the top, click Analyze. So up at the top, click Analyze. Up at the top, click Analyze. Up at the top, click Analyze. We are comparing means. So compare means. Analyze, compare means. Analyze, compare means. Analyze, compare means. We are running an independent samples t-test because we have a between subjects design. Between subjects design, independent samples t-test. So analyze, compare means, independent samples t-test. Click the box. Test variable. You put your dependent variable there. This causes that, okay? So what you measured. Dependent variable is your measure. Manipulation, your grouping variable. That is your independent variable, right? What you are grouping the free will prejudice data on is your independent variable. The SPSS calls it the grouping variable. It's just a program. We'll get used to it, right? There's multiple words for multiple ideas in stats. Now, defining my groups. I need to ask myself a question. I'm going to take my value labels off. I'm actually hit cancel for a second. View value labels. I want those off. Before I define my groups, I want to figure out which group am I predicting to have the higher mean. Well, I talked about this earlier. I predict that participants who hear the everyone can overcome prejudice message will have higher beliefs in free will. So the group that I believe that will have the highest mean will be the group 1 in when I define my variables. So let me show you this because there is 1 and 2 here. You do not have to define your groups based on your 1 and 2 over here. So my first group is going to be 2 because I believe that the folks that were in the everyone can overcome prejudice group, you can see 5, 3, 4, 4, 5, 3, 4, 4, 2, 2, 2. I believe they will have higher beliefs in free will than folks in the everyone is prejudice group. So group 2 is then the other group by default. I click continue. Make sure your estimate of effect sizes is clicked right there. I click OK. And I'm going to show you some stuff real quickly. What do I get? I get everything I need. Means of both groups. Everyone can overcome. Everyone is prejudiced. They're labeled nicely. Standard deviations in both groups. Standard error of the mean, which you don't need to think about. I get Levine's test for equality of variances. This is important. If Levine's test is significant, you have to use the bottom row. If Levine's test is not significant, P's greater than 0.05, you use the top row. So today we're going to use the top row. We get a T statistic, which you don't know what that is yet. You got a degrees of freedom, which you don't know what that is yet. Both of those are used to get your P value. Your P value is 0.032. You know your true population mean difference is not 0. Your sampled mean difference is 1.75. Your standard error of the difference, that's the standard error of the random sampling distribution of the mean difference. Standard error of the difference, right? That's that standard deviation in that normal shaped curve where the p-value comes from. 95% confidence interval of the mean difference. That's the true population mean difference likely falls in that range. Now, additionally, what do we get? We get our Cohen's d calculated, or we get our standardizer of our Cohen's d. So that's the average standard deviation. If you look, it looks very similar. We get our, we get our point estimate. That means our Cohen's d point estimate. That's our Cohen's d, 1.967. We get our 95% confidence interval of the Cohen's d, which is our Cohen's d could be from a small effect in line with our hypothesis to a large effect in line with our hypothesis. When I'm looking at this data in terms of the population, what do I know? My true population mean difference is not 0. I know that my true population effect may be a small effect to a large effect. I should really improve my precision of my methods, particularly for this case, because I'm developing an intervention to try to reduce prejudice. I don't want my activist friends to use my intervention and waste their time and not get any closer to really increasing beliefs in free will over prejudice. If they want to, if they believe that's important. But ultimately, that's the data. And you actually know how to interpret all the important aspects. You just don't know what the t-value and degrees of freedom are. But I'll explain that to you in a second. And ultimately, you don't really need to know it, because all you're getting with this is that your true population mean difference is not 0. That's where your p-value comes from. So we are done, and that is how it works. Those of you that are using an older version of SPSS, you're going to have to stick around to the end of the lecture. I'll show you how to get your Cohen's d information. It's going to be more work. So that's it. That's how we analyze data. Okay, we have our data. Let's start interpreting it. So we care about two things when we're looking at our data. Number one, we want to be able to describe our sample data. We call these descriptive statistics. And if you notice that the font is kind of changed, we care about making inferences about the true population parameters, inferential statistics, truth, right? There's a difference here. Descriptive statistics we need, we use them, but we really care about these inferential statistics. So let's go over our descriptive statistics first. First, we look at our output. We can see that in the overcome condition versus the everyone is condition, we have two different means. So the overcome condition had a mean of 4. The everyone condition had a mean of 2.25. This is in line with my hypothesis. We also can see the standard deviations. What I'm looking for there is, okay, was one of my conditions worse than the others? So we have a 0.81 versus a 0.95. The overcome condition had a little bit less error in measurement than my everyone overcame condition. And there's a test that we're going to be able to do to see if that actually matters, but not yet. We're just looking at our descriptive statistics. Okay? Then the next important descriptive statistic is our mean difference. Our mean difference is 1.75. If you followed along with me and set everything up correctly, your positive numbers support your hypothesis. My hypothesis is correct. My positive mean difference suggests that people in the overcome condition had higher beliefs in free will than people in the everyone is prejudice condition. And if you're noticing differences between the output I just got and this output, that's because I redid my SPSS a few times to make it faster and shorter. So just know it's the same data, it's the same output. And then finally, Cohen's d is also a descriptive statistic. Our Cohen's d is 1.967. It's the point estimate. That standardizer is just the average standard deviation. It's actually the pooled standard deviation. I'll explain that to you in a second. But ultimately, this is how it works. And remember I said our standard deviation is now Bessel corrected. So instead of dividing by 4, these standard deviations, that step in there was divided by 3, n minus 1. So when you're calculating the variance, you divide by 3, not 4. And we call that the Bessel correction. And that just gives us a better approximation of the population standard deviation. So we use it because population approximations are truth. Okay, so that's our descriptive statistics. It's not that complicated. Everything in there is great. That's perfect. Let's go on to our inferential statistics, inferring truth, inferring the true population mean difference. So let's go ahead and look at this output. First thing we have to look at is that big black box, that whole thing. It's called Levine's test. Levine's test for equality of variances. Now, earlier I said we had two different standard deviations across our two different conditions, and we want to know if one of our conditions was significantly worse than our others in terms of error. If it is, we use the bottom row. You see equal variances assumed versus equal variances not assumed. So what we're looking at here is the p-value. This is a p-value. Our p-value here is greater than 0.05, so the true population standard deviation difference very well could be 0. So we're going to assume equal variances and use the top row since our p-value here is greater than 0.05, and that suggests that we have not disproven that our two population standard deviations are different from each other. If this p-value was less than 0.05 in the black box, if that p-value was less than 0.05, then we would use the bottom row. We would say our standard deviations, our variances, they're related. Remember, standard deviation squared is variance. Our variances or standard deviations are significantly different from each other, so we cannot assume equal variances. This p-value is telling us if the true population mean difference for standard deviations is 0 or not, essentially. If p is less than 0.05, we say that our variances are not the same, so we use the bottom row. So if your p-value is less than 0.05, the population mean difference for standard deviations is greater than 0, and we have to use the bottom row. That's it. Same idea. It's just a p-value that's testing the mean difference between standard deviations. But let me just give you what you need to know quick and dirty there. If that p-value in the Levine's test is 0.05 or less than, use the bottom row. If not, use the top row. T, degrees of freedom, p-value, not going to explain T yet, not going to explain degrees of freedom. It leads to our p-value, 0.032. Okay? So we have statistically disproven the null hypothesis. We are fairly certain and confident that our true population mean difference is not 0. What do we know about our mean difference? It's positive, right? So it makes sense for us to conclude that those that read the article about overcoming their prejudice, or that everyone can do that, they had higher beliefs in free will than those who were told everyone is prejudiced. You can see that in my labels in the descriptive statistics. Okay? Now we're saying, well, what are the possible true population mean differences that could exist? Not just is it not 0? We know the population mean difference is not 0, but the true population mean difference could be anywhere from 0.2 to 3.28. Could be anything between that range. Well, I struggle to interpret those, so I like to look at my 95% confidence interval of my Cohen's d. That's the first row right there, Cohen's d. We talked about this. This is your average standard deviation. We call it pooled now. This is our Cohen's d. It's hidden right now, but our 95% confidence interval suggests that our true population mean difference could be a very small effect or a very, very large effect in favor of our hypothesis. We know that the true population mean difference is not 0. We know it's greater than 0. And we know that true population mean difference likely falls between 1.58 and 3.68. Perfect. We know everything we need to know. Isn't that great? And that's why the conceptual unit was done, because this is what we needed to figure out. Okay, so review. When you got this data, if you just want a set of steps, look at your means and your mean difference. Was your hypothesis supported? Yes, in this case. Look at your Cohen's d to understand if your effect is small, medium, or large in our field. So that's descriptive statistics. This one, I believe, was 1.7. So that descriptive Cohen's d was 1.7. So that suggests a large effect. Then the next thing I did was check my Levine's test for equality of variance. And what did I find? I found a non-significant test, so I used the top row. If I found a significant test, a small p, I would use the bottom row. So then I check my p-value to see if we have rejected, statistically disproven, the hypothesis that your population mean difference is 0. Yes, we did. Our p-value is 0.03, if my memory serves me correct. I checked my 95% confidence interval of the mean difference, but really I looked at my 95% confidence interval of Cohen's d. And essentially what I found there was that I did have a difference, an effect that is greater than 0, that my mean difference is positive, but my true effect could be really small, or it could be really large. I need to improve my methods in my study to get a more precise estimate of the truth I'm seeking. But right now, that's everything that we need to know, right? And I have some suggestions here. Does your estimate only cross 2 or 1 levels of interpretation? That's good. 3 levels, that's okay. It's not great. It could be meh. 4 is poor. Anytime your 95% confidence interval of the Cohen's d crosses 4 levels of interpretation, then you really don't know anything. Oh, it could be a small effect against my hypothesis, could be a no effect, could be a medium effect in favor, small effect in favor, medium effect in favor. I don't really know anything at that point. Or you can imagine, it could be a null effect, it could be a small effect in favor, medium effect in favor, large effect in favor. I don't know anything at that point. Essentially, yeah. And also remember, a 95% confidence interval of Cohen d can be not significant but precise. So this one right here suggests that my true population mean difference is a small effect against my hypothesis or a small effect in favor of my hypothesis. These are really tiny, tiny, tiny small effects. I'm going to state that if I found this 95% CI of Cohen's d, that essentially I'm pretty sure that my true population mean difference is basically 0. So presentation. Today we're just going to focus on writing. The lab focuses on graphs. When you do make graphs of a t-test, you put your means in there, your 2 means, and your 2 standard errors of the means that I said you can forget. So not the standard error of the mean difference, but the standard error of each of those means. That's just kind of standard. It doesn't really tell us much, but ultimately we're not going to make graphs for a t-test. Writing your results in psychology. What do we need? What do people want? They want the means. They want the standard deviations for future meta-analysis. They want your t-statistic. They want your degrees of freedom. People expect this. I'll explain that to you shortly. You include your p-value. People want to know if you disprove the null hypothesis that your population mean difference is 0. You're never going to forget what that is. Include your 95% confidence interval of the mean difference because this likely contains the true value we seek. This is truth. And then also include your 95% confidence interval of Cohen's d. And this is for you to help you interpret what you found. Do you have precise estimate of truth? Did you have bad science? Do you have a useful effect? All these are questions you can answer with the 95% CI of Cohen's d. Punctuating statistical sentences in APA style is kind of a pain. And so these are some rules that I got directly from the APA style blog to help us out. Use parentheses to enclose statistical values, right? This is an example from them. Proved to be statistically significant. P in parentheses, P equals 0.42. Use parentheses to enclose degrees of freedom. So you see a T with a number after it. That's its degrees of freedom. You see an F. You don't know what that is. Those are degrees of freedom. The brackets to enclose limits of confidence intervals. 89% CIs. They didn't use 95%. They used 89. 3.45, 2.7. Negative 6.0, 3.89. And negative 7.23 and 1.89. Use italics for statistical symbols other than vectors and matrices. So every statistical symbol we use is italicized. Use an italicized and lowercase n to refer to the sample population. Uppercase n refers to the population sample size. So that would be 8 billion humans. If a value has the potential to exceed 1, use the leading 0. So Cohen's d, you got to use the leading 0. If a value can never exceed 1, do not use the leading 0. Cohen's d here, written out. These are just sort of like a dictionary. So these are statistics. This is how you can abbreviate it: plural, singular, singular, plural. There's just a bunch. This is useful. Take a screenshot of this. Take a screenshot of this, and that'll help you out. So what do we do with this information? We make two perfect statistical sentences. The first sentence is all the stats. The second sentence is one I want you to do, where you interpret your inferential statistics, because you need to really get good at knowing that a p-value is testing if your population mean difference is 0, all that stuff. So we'll go through that together. How would I write up my statistical sentence? Participants assigned to the everyone can overcome their prejudice article reported statistically higher beliefs in free will over their prejudice. Then look, what do I got there? Parentheses, mean, it's italicized, equals 4.0. Standard deviation, which can be greater than 1. So 0, parentheses, italicized, equals, the equal sign is not italicized, equals 0.82. Then individuals assigned to the everyone is prejudiced article. We have the same thing with the means and the standard deviation, and then I add a semicolon. Why? Because I'm adding a new statistic, the t-value. So t with 6 degrees of freedom equals 2.78, p equals 0.032, and d equals 1.97. Now, the degrees of freedom were in the output. I didn't talk about them, but they were there. T, degree of freedom. I said, here's your t score, here's your degrees of freedom. You'll see them. They're right next to each other. My 95% confidence interval of my Cohen's d, right? Because why did I put these together? The t-value is associated with the p, right? That's done. Then another semicolon. D equals 1.97. See, D is italicized. Equals 1.97, comma, 95% CI in brackets, 0.23 to 3.69. Those Cohen's D's very much can be greater than 1. And then the mean difference equals 1.75, 95% CI equals 0.21, 3.29. And that's all the statistics we need. And that's exactly how you write it up. So that literally all that work was for one sentence in your paper. Now, additionally, because you are learning this right now, and I don't want to make you write a whole method section yet and results section yet, I want you to interpret your results. These results indicate that messages suggesting everyone is prejudiced reduce beliefs in free will over their prejudice in comparison to messages suggesting everyone can overcome their prejudice. So right now, I'm just providing my overall interpretation of the data. I do have clear evidence that my intervention works. If your intervention doesn't work, you can say do not indicate. The p-value suggests that the true population mean difference is unlikely to be 0. However, the 95% confidence intervals suggest that the true population effect is likely to fall between a small effect with very little impact and a large effect with tremendous potential for changing these beliefs. While we are actively attempting to improve our methods to reduce noise and error with the hopes of providing a more precise estimate, activists and educators should refrain from applying this intervention in the real world, as it may only lead to the tiniest gains in belief in free will over one's prejudice. Right? I want you to do that. So that first sentence in sentence number 2 plus was just me describing the direction of my means. Then I use the p-value suggests that the true population mean difference is unlikely to be 0. However, the 95%, I go right into the p-value and give the interpretation. That's for me. You're doing this for me, for you. This is going to help you know what you're doing. However, then I interpret my 95% CI of the Cohen's d, and I provide a real-world take-home point. What I also want to point out is if you look above here in the first sentence, I didn't mention this, I use the word statistically higher. Some people use statistically significant. Some people just use the word significant. I don't think significant is really, I think it's confusing people that are reading our science, confusing scientists. So I don't personally use it. You can use it. I wrote statistically higher. That is true. And that statistically higher means my p-value is less than 0.05. So that's everything for this example. You're going to want to adapt it for your own problems. Okay, everything that we've just learned would allow you to publish your paper in the best journals in psychology, right? You just don't know what a few things are. Let's go over those real quickly. Bessel's correction, it is the standard deviation. You divide by n-1 because it gives a better estimation of the population standard deviation. That's it. That's all you need to know. You don't even need to really put this in memory, but this is for curious students that are like, why are we doing this now and not the way we did it before? The way we did it before was so it made sense. This is now those statistical corrections in our formulas that would not make sense to us if we didn't know the goal is to find true population parameters. In this case, we want a true population standard deviation too. So after that, we get our pooled standard deviation versus average standard deviation. I'll describe that real quickly. Degrees of freedom, t-score, and the t-distribution. So let's go in with pooled standard deviation versus average standard deviation. All right, so we know the average standard deviation. We know its function in the Cohen's d, right? We know that it means error, average, or pooled standard deviation. That's not a division sign, that's an or. And essentially what do we see here? What's the difference between the two calculations? So pooled standard deviation, why are we using it? It's a better estimation of the population standard deviation that we're seeking. So it's the same reason we use the Bessel correction. It's the same reason we use the average standard deviation, or pooled standard deviation. Conceptually, it is the average standard deviation. If you look at the end result of both of these examples, it's the same. The difference between average and pooled standard deviation only matters when your sample sizes are different. So what does it do? Well, okay, so it looks like the equation for time travel. There's a square root in there, great. There's an n-1 for the control group. There's an n-1 for the experimental group. There's a denominator of n control plus n experimental minus 2. Okay, so this is just looking real funky, right? Well, let's talk about it. So we got the variance of the control group. We're looking for the average standard deviation. What do we know about variance? The square root of variance is standard deviation. So now you understand the square root, why that's there. So that's there to eventually get rid of the squared the squared units of deviation. We see our variance calculation there for the control group and our variance calculation for the experimental group. We see we're multiplying it by n-1 for both of those groups. What you don't see, because the denominator got simplified, is that is really dividing by n of the control minus 1 plus n of the experimental minus 1. That just works out n of control minus 1 plus n of experimental minus 1. All in one equation is just n of control plus n of experimental minus 2. So what you're doing is what we call a weighted average. Now you're weighting how much the variance of the control group and the variance of the experimental group get calculated into the average deviation, and you're weighting it on the sample size minus 1. So if you have a group that has a sample size of 100 and another group that has a sample size of 10, essentially that variance of the group with 100 is going to be weighted basically, not exactly, 10 times more than the standard deviation of the group with only 10 observations, right? So what we're doing is we're just weighting our average standard deviation calculation based on our sample size. And so this is the formula. This is how it works. You know, it's just a weighted average. It's sample size minus 1, and you'll understand that in a second. Now, degrees of freedom is a difficult concept for undergrads to grasp, and it's a difficult concept for many psychologists to grasp. In fact, most people just are like, oh, degrees of freedom is a formula for degrees of freedom. So here's the actual definitions. The first one makes no sense to me. The number of independent values or quantities which can be assigned to a statistical distribution. That makes no sense to me right now, not from a teaching perspective. The next definition I can deal with. The number of independent values that can vary in an analysis without breaking any constraints. Well, really, we only have 2 constraints in our data. Those constraints is that mean 1 equals mean 1 and mean 2 equals mean 2. Everything else is pretty much based on the mean. So essentially what we have here is a riddle. And this is my degrees of freedom riddle. And this really works well for t-tests and ANOVAs. Assume that a number set is predestined to have its sampled means. If you wiped the values of your observations and only had to meet the assumption clearly of the sample means, how many of your observations are free to be any number? The number of free observations equal your degrees of freedom. That's the riddle. Let's see it in practice. All right, so here's our data we've been working with. What is the degrees of freedom riddle? It states basically if the means have to be 2.25 and 4, but the other numbers can be anything in the world, how many of them are free to be anything in the world, and how many of them are fixed so that the means are still 2.25 and 4? So in this example, right, we're saying get rid of those means. Those can be anything. I'm just going to choose some random numbers that I'm interested in to be the data that we've just erased. We're saying, imagine we don't know that data. How many observations in this data set are free to be anything and still have our two means equal 2.25 and 4? So let's just play around with that. Well, I was like, okay, I chose 23 to be my first number because I'm kind of watching that Jordan doc. I chose 6 randomly. You can choose whatever number you want. I chose 23. I chose 6 because I wanted to. So those were free to vary. I still have 2 numbers to determine. I chose 84 for a personal reason. And then I'm stuck with that last number. That last number is forced to be negative 104 so that my mean is still 2.25. So ultimately 3 of those numbers were free to vary and 1 was not. Now, when I look at the second group, I chose 24, 7, 85. Those were free to vary. And then finally, I was forced to choose negative 100 to find that mean of 4 that is in the everyone can overcome prejudice group. So ultimately, I have 6 total numbers that are free to vary. And you'll see that. Let me highlight that. These were numbers that I chose. The green ones were the green numbers are the numbers that I chose, and the red numbers were numbers I had to choose so that the means worked out to be correct. Now, we've seen the normal curve before, and you know the normal curve. The normal curve is on this graph in red. You've seen that. The t-distribution is basically the same thing. It's the same idea, has the same intellectual and logical properties. It's not perfectly identical. I'm not saying that. You can see that there is, the difference is that it's a little drop. The t is a little bit lower than the normal curve, and you can see that the tails are a little bit more bloated in the t-distribution than they are in the normal curve. But ultimately, when we run a between subjects design and an independent samples t-test, we don't use the normal curve because the t-distribution is actually closer to the true population random sampling distribution of mean differences. So that idea from before with the random sampling distribution of mean differences is still present. The shape has just changed from normal to t. Why? Because the t-distribution better represents the true population shape due to our Monte Carlo studies. So all I'm saying is the curve's changing slightly. We're using a different curve. I want to talk about the t-distribution a little bit. So first, what I find to be really interesting is that t-distributions change based on your sample size or your degrees of freedom. Remember, degrees of freedom is basically your sample size minus, in this kind of experiment, in a 2-group experiment, it's your total sample size minus 2. Those are your degrees of freedom. You know why now. But essentially, degrees of freedom and sample size are very highly correlated, right? Okay. So you're with me on that. Well, what's cool about the t-distribution is it penalizes small sample sizes. And so that's in part why it helps lead to better and true random sampling distributions of mean differences. Because when you have small sample sizes, you have more error. We're not going to use the normal curve when we have small sample sizes. We should really adjust for the fact that we have small sample sizes and more error in our random sampling distribution of mean differences when the null is true. This is really just a low-level detail that I enjoy. You don't have to worry about it too much. But essentially, that dotted line is the normal curve. And what happens when our sample size falls, when it gets lower and lower and lower? You can see the peak drops and it drops and it drops and it drops. And I have different degrees of freedom listed on the right. And what you also notice is that the area in the tails gets larger and larger and larger and larger. Remember, the area in the tails is where your p-value comes from, and you want that small. So now you have a penalty for small sample sizes, and this is why we use the t-distribution. You want to get over that penalty for small sample sizes? Use large sample sizes, right? But imagine that blue line, I sampled a mean difference of, like, let's say negative 2.75. My p-value when I have 1 degree of freedom, which is like 3 observations, it looks like it would be like 25%, right? My p-value when I have 4 degrees of freedom, which would be 5 observations, looks to be about 20%. You go up to 12 observations, it's probably dropped down to 10%. You go to 20 observations, it's dropped down to maybe, well, a lot lower than that. My percentages are off, but it drops down even more. And then when you have the normal curve, you basically have no percentage there. So you can see that, like, what would happen to your p-value is that when you have small sample sizes, it gets larger and larger and larger because you're using the t-distribution. If you were using the normal curve, it would look like a really big, massive effect, but it's not. So I just want you to know that the t-distribution changes based on your degrees of freedom, which is a mathematical understanding of sample size. And the t-distribution penalizes small sample sizes. So how do we use the t-distribution in practice? Well, essentially, for our p-value, it's just like the example we did to figure out the definition of p-value, except the shape is a t-shape, not normal. Now, one of the things you'll notice is that instead of mean differences has my x-axis or my number line, I have t-scores. Well, that's because you can easily convert a mean difference to t-scores, and this is how we present this information in a standard way. So I'll explain t-score to you in a second, but essentially one way we use the t-distribution is we just set the null to be true, and we can then use this to figure out the probability of sampling any mean difference from negative infinity to positive infinity, even though they're not shown on this graph. So everything on the left is what we learned last in this class. Now on the right, I never really talked about where the 95% confidence intervals of the mean difference came from, because it was hard enough to get us to interpret them, right? It's a difficult task. So now we can add some knowledge here. Essentially, we take our sampled mean difference, we plop a t-distribution right on top of it, and then we find the middle 95%, and we know that most of those intervals will contain the true population mean difference we seek. We know, in fact, that 95% of 95% confidence intervals contain the true population mean difference. So the one on the left we just use, does our sampled mean difference suggest that our true population mean difference is not 0? That's a p-value. On the right, we apply the t-distribution right on top of our sampled mean difference to see what the true possible mean differences could be. So what is the t-statistic formula? Conceptually, we got to think about this because we already have it calculated. Let's just think about what it's showing us. So we got a sampled mean difference. That's our signal, our experimental signal, minus the mean difference if the null were true. Well, we know that's 0, okay? That's not 99.9% of the time it's 0. Sometimes it's not. We're not going to get into that 0.01% of the time, okay? But essentially, we're looking at a difference between the signal we found and the signal predicted if the null were true, divided by our standard error. Well, our standard error is the standard deviation in the random sampling distribution of mean differences if the null were true. So this is very similar to a Cohen's d, right? We're looking at our ability to see a difference from the null hypothesis given the noise in our sampling of means from the population mean difference when the null hypothesis were true. So it's really super complicated here, but what I want you to see is it is another measure of signal to noise. The signal is our ability to see a difference from the null, so that's where it's kind of special, right? It's not just the difference between our two means, it's the ability to see a difference in our signal from the null, right? How big that difference is, our mean difference minus the predicted mean difference of 0, right? Divided by our standard error which is the error in sampling mean differences when the null is true from a population. So essentially, it's another measure of signal over noise. It's just really the noise is noise in our ability to sample the population mean difference when the null is true. If that doesn't make sense, that's fine. I want you to see it's very similar to Cohen's d. If you don't, and you want to talk about it, let's talk about it. It's not the end of the world. But what you do need to realize is that this is the same stuff we were doing in the conceptual unit. We're just converting a mean difference to a t-score so that we can then figure out our p-value. And that's the most important thing here. So now let's look at this statistic. Let's look at some more numbers. There was a request for some more numbers. So I'm going to show you some numbers here. So t, sampled mean difference, minus mean difference if the null were true, divided by standard error. What does this look like in terms of symbols? Your control group minus experimental group, or those can be flipped. Y'all have started to realize that, I think. Your mean difference, you can set it up either way, but I had to choose one. So that's how I chose to do it, because I like talking about control and experimental effects. Minus the null being true divided by standard error, which is S pooled, which we already know. That's that average standard deviation corrected for different sample sizes, multiplied by this very simple correction factor. So if we simplify that, we know that the mean difference if the null were true is 0. So we can simplify that component. We're going to go on. We're going to simplify this a little bit more. Your t equals a mean difference minus 0 divided by S pooled times the sample size correction. What you notice is that mean difference divided by S pooled is Cohen's d. So essentially we have Cohen's d divided by the sample size correction factor. So if we want to find Cohen's d from a t value, we take our t value times the sample size correction factor. If you're only given one sample size, you just have, like if you're told the total sample size, go ahead, like it's 100. All you do is have to take the square root of 1 over 100. Multiply that by your t, and that's going to get you your Cohen's d. This is how you're going to start figuring out when you're reading articles if the t statistic matters, if it was a strong effect. So it's just a fun little calculation trick. Also, really easy to calculate your t statistic. Cohen's d divided by the correction factor. You already know how to get Cohen's d. So there you go. Your homework is just to analyze these 3 data sets, right? And I want everything. I want for each data set, I want your final write-up and your SPSS outputs. I want those. Data set 1, seniors in college versus freshmen in college. Dependent variable is optimism. You can choose your own hypothesis there. So I will have 2 sets of answers that are correct. My hypothesis that I'm going to choose is that freshmen are more optimistic than seniors. Data set number 2 is independent variable Republicans versus Democrats, how much they like pie. With this one, I don't really have a hypothesis, and that's fine. I don't really care which one you choose to be the first group or the second group. So, some people are going to have a negative mean difference. Some people are going to have a positive mean difference. I just think it's hilarious. Yeah, it's funny. Online versus in-person education, dependent variable scores on a standardized test of knowledge. I do believe that in-person is superior. So you might believe online is superior until this semester, maybe, I don't know. You can have your own hypothesis there. Just make it clear, whatever that hypothesis is, that you're stating it and you're setting your SPSS data to show me positive mean differences are supporting your hypothesis. One standalone problem, your t value is 5. N1 is 25, N2 is 25, okay? I want you to convert that t to just one Cohen's d, just this one time. That's the only calculation I'm asking you to do. This is the end of the lecture. After this lecture, after you do all 3 of these data sets and you get the correct outputs, you have passed a very important analysis ability. I have given you some extra stuff, the calculation, equations. To calculate t, it's just Cohen's d divided by that correction factor. That's actually a pretty easy calculation from stuff you already know how to do. I'm going to rely on past knowledge. We're not going to build everything from the ground up. We know how to calculate Cohen's d. We know where it comes from. So ultimately, for you to be successful in stats, you need to be able to get the numbers, interpret the numbers, and write them up. Let's practice that. So good work. Not a super long lecture, not a super short lecture, in the middle, but we are through with it. Next lecture will be a lot shorter. Those of you that do not have the newest version of SPSS, you're going to have to calculate the 95% confidence interval of Cohen's d via this Excel file that was created by Daniel Lakens, who's a pretty well-known statistician. So it provides a lot of effect size measures. But first one, is this a t-test? Yes. Is a comparison between dependent samples? No. Do you have the means and standard deviations and ends? Yes. And so then what we have to do is we have to say, okay, group one, that needs to be our everyone can overcome prejudice group mean. Group two, everyone is prejudiced. So we got to put all our numbers in here. You can see I've done that already, right? I've put my numbers in. And then it gives us a 95% confidence interval of the mean difference. It gives us a Cohen's d value. And then from that, I did calculate standard deviation pooled. I calculated the lower and upper limits. You're going to notice that yours are different than the ones in SPSS. And the reason why they're different is that the ones in SPSS don't use a central t-distribution. They use this funky t-distribution. So this is the exact way that I was teaching you all to think about it in class. Now, the SPSS version is more accurate and correct, but you're not that far off. You're just a little bit higher than their estimate here and a little bit lower than their estimate here. So that's okay. But essentially, all you have to do is put your numbers in, and these will update. For example, look, I'll just change one number, and you can see that all the numbers updated here. So you need, this is your 95% confidence interval of the Cohen's d. Here's one limit. Here's another limit. Here's your standard deviation pooled. Here's your Cohen's d. That's what you're going to have to do to get it. You're going to get this Excel file from our D2L page. So that's all we got. Get it from our D2L, our website, and you'll be able to calculate this if you're in the boat, if you're in this boat.